Section: Introduction. In this section, we discuss how latent diffusion models, LDMs, enable high-resolution image synthesis through a denoising diffusion process in a compressed latent space, which is efficient for various applications. However, we face a significant challenge. The generation process is unstable, leading to inconsistent results. Even minor changes, like pixel shifts, can drastically alter the output images. To tackle this issue, we aim to enhance the shift equivariance of LDMs, which is crucial for tasks requiring stability, such as video generation and normal estimation. We analyze the widely used stable diffusion model, focusing on how shifts in the latent space should ideally correspond to shifts in the decoded images. However, we find that aliasing effects hinder this ideal behavior. We identify several reasons for this instability. The aliasing can worsen during training, the iterative denoising process accumulates aliasing, and self-attention operations in the UNet are not shift equivariant. To address these challenges, we propose two key improvements. First, we introduce an equivariance loss that optimizes the model's performance by directly addressing the error between shifted outputs and their corresponding inputs. Second, we develop a fully equivariant self-attention mechanism that maintains consistency during shifts. With these enhancements, we present the Alias-Free Latent Diffusion Model, AFLDM, which demonstrates improved shift equivariance throughout the generation process. Our experiments show that AFLDM is robust against irregular pixel shifts, motivating us to propose a warping equivariant video generation method that models frame deformations effectively. Additionally, AFLDM generalizes well to other image-to-image tasks, such as super resolution and normal estimation. In summary, we have identified and addressed the critical limitation of poor shift equivariance in LDMs. By adapting alias-free design principles, we have developed AFLDM, which shows significant promise in generating consistent results across various tasks. Section Summary. In this section, we explore the limitations of latent diffusion models, LDMs, regarding shift equivariance, which affects their ability to generate consistent images and videos. We introduce the Alias-Free Latent Diffusion Model, AFLDM, which incorporates an equivariance loss and a modified self-attention mechanism to effectively mitigate aliasing effects and enhance stability across various image synthesis tasks. Section: Related Work. In this section, we discuss related work in the field of diffusion models. Diffusion models are a type of generative model that convert random Gaussian noise into clear images through a step-by-step denoising process. Early versions of these models performed the denoising directly on images, which required many steps, sometimes up to 1,000. While they were effective, they faced criticism for their lengthy training and inference times. To address this, we look at latent diffusion models, LDMs, which speed up the process by breaking it into two stages, generating a latent representation and then decoding it into an image. Despite improvements in various aspects, such as the underlying network and training goals, the two-stage structure is still essential. Our experiments indicate that existing LDMs struggle with instability due to aliasing effects. When we compare LDMs to generative adversarial networks, GANs, we notice that LDMs are particularly unstable, especially regarding smooth latent spaces and shift equivariance. A smooth latent space allows for gradual changes in generated images when we interpolate between latent representations, which is beneficial for applications like image inversion and interpolation. Shift equivariance ensures that generated outputs remain consistent even when input objects move within a scene, which is vital for maintaining coherence in video applications. Common strategies to reduce instability in diffusion models include preventing image overfitting, using cross-frame attention, and applying regularization techniques. However, the shift equivariance aspect of LDMs is still not well explored. Next, we address alias-free neural networks. Aliasing occurs when signals overlap due to improper sampling, which can hinder neural networks by reducing their shift equivariance and shift invariance. Initial attempts to create alias-free networks focused on enhancing the shift invariance of classification convolutional neural networks, CNNs, through better downsampling methods. Later, Style-Gone-3 highlighted that the processes of upsampling, downsampling, and nonlinear operations in neural networks are not free from aliasing and introduced Kaiser filtering as a way to better approximate ideal signal processing. Following this, Alias-Free ConvNets, AFC, built on Style-Gone-3's work by replacing Kaiser filters with operations based on the fast Fourier transform, FFT, and using polynomial n-online arities. While much of the previous research has concentrated on aliasing in classification CNNs and GANs, there has been limited investigation into aliasing effects in LDMs. We also introduced Stable Diffusion, SD, which is a latent diffusion model that combines a variational autoencoder, VAE, with a text condition denoising UNet. Initially, the encoder and decoder of the VAE are trained to minimize the difference between the input image and the reconstructed image. The latent representation is downsampled, and then a denoising UNet is trained to clean the noisy latent representation at each time step. During the sampling phase, we generate a clean latent representation through a reverse diffusion process, which is then decoded to produce the final image. Both the VAE and UNet utilize an encoder-decoder architecture with similar components, including ResNet blocks and self-attention blocks. While the networks rely heavily on shift-equivariant convolution layers, other components, such as n-online arities and self-attention, do not maintain shift-equivariance. In our exploration of Style-Gone-3, we note that it generates high-resolution images by gradually upsampling a low-resolution feature using a CNN-based synthesis network. Despite the high quality of the generated images, the original Style-Gone suffers from a texture sticking effect, where details in the output remain fixed in position when the input feature shifts. Style-Gone-3 attributes this issue to aliasing in the synthesis network and analyzes it through a continuous signal perspective. Each feature in the network corresponds to a continuous signal, and if a network layer is shift-equivariant, its effects should be consistent across both discrete and continuous domains. Based on this understanding, Style-Gone-3 implements several key improvements, including transforming the input to Fourier features, cropping border pixels to prevent absolute position leakage, using Kaiser filters for ideal resampling, and applying filtered n-online arities to manage high frequencies. Lastly, we discuss fractional shift equivariance. We define a shift operator that moves an image by a certain number of pixels, and we say that an operator is shift equivariant if it behaves consistently under this shift. We extend this concept to fractional shifts, allowing for more nuanced image transformations. In our work, we implement this as a Fourier shift, which adjusts the phase of an image in the Fourier domain. We also consider how to handle edge pixels when shifting, using a cropped shift method that fills in missing pixels with a constant value, aligning with the default padding mode of convolutional layers. Section Summary. In this section, we discuss the evolution of diffusion models, particularly latent diffusion models, LDMs, which improve efficiency by generating images in a latent space but face instability issues due to aliasing effects. We also highlight the importance of shift equivariance for maintaining consistency in generated outputs and introduce techniques to mitigate aliasing, while noting that the exploration of these effects in LDMs remains limited. Section: Alias-Free Latent Diffusion Models. In this section, we describe the architecture of our alias-free latent diffusion models, AFLDM. Both the variational autoencoder, VAE, and UNet in our model follow an encoder-decoder structure. We implement ideal upsampling, downsampling, and filtered nonlinearity. Our main goal is to enhance the fractional shift equivariance of the diffusion model, which is important for its various applications. While Style-Gone-3 offers a good approach for creating alias-free convolutional neural networks, CNNs, we cannot directly apply these methods to our diffusion model. This is because Style-Gone-3's generation process relies solely on the latent-to-image synthesis network, allowing for flexible designs related to equivariance. In contrast, the equivariance in our latent diffusion models, LDMs, is influenced by the encoder, decoder, and UNet together. The latent representation is generated by the encoder, which limits our ability to redefine it, especially since self-attention mechanisms are sensitive to small changes. To address these challenges, we introduce AFLDM, which includes two key improvements. First, we create a continuous latent representation that has a limited frequency bandwidth, naturally supporting fractional shifts. We achieve this by modifying network components with anti-aliasing designs and incorporating an equivariance loss during training. Second, we enhance the equivariance of self-attention by using equivariant attention, which keeps the key and value features fixed when processing shifted latents. Some of our anti-aliasing techniques draw inspiration from style GON3. We define a LDM pipeline as fractional shift equivariant if certain conditions hold true for the transformations applied to the latent variables. Specifically, we ensure that the latent representation can be sampled everywhere by applying discrete Fourier transform, phase shifts, and inverse discrete Fourier transform. For instance, if our input image has a resolution of S by S, the maximum frequency of the latent should be less than S divided by 2 times the downsampling factor. We find that incorporating anti-aliasing layers significantly improves the shift equivariance of a randomly initialized autoencoder. However, as training continues, we notice a decline in this equivariance, likely due to imperfect anti-aliasing designs that allow aliasing effects to interfere with the learning process. To tackle this, we focus on regularizing the network's learning by optimizing the error between outputs from shifted inputs and their corresponding shifted outputs. We propose an equivariance loss that measures this error and integrates it into the original training loss. For the VAE, we compute the equivariance loss for both the encoder and decoder separately. We define the loss based on the input and the transformations applied. For the UNet, we define the equivariance loss for the latent representation at each time step, ensuring we account for the effects of padded pixels during the denoising process by using circular shifts. Overall, our modifications lead to a continuous latent representation that closely resembles a band-limited signal, enhancing the performance of our alias-free VAE. Section Summary. In this section, we introduce the Alias-Free Latent Diffusion Model, AFLDM, which enhances the fractional shift equivariance of standard diffusion models by implementing a continuous latent representation and equivariant attention mechanisms. Our approach incorporates anti-aliasing designs and an equivariance loss to improve the model's performance in generating high-quality images while addressing the limitations of existing methods like style GON3. Section: Equivariant Attention. In this section, we introduce equivariant attention, EA. We start with an input image token sequence, which we denote as X, and define the self-attention operation. This operation involves applying a softmax function to a combination of projections of X, resulting in a new representation. While self-attention is naturally shift equivariant for circular shifts, it struggles with cropped shifts or non-rigid deformations, like warping. To maintain equivariance, we need a specific relationship between the shifted and original representations, but cropping disrupts this relationship. To solve this issue, we redefine self-attention as a pointwise operation, ensuring it remains equivariant under any relative shifts to a reference frame. We formally define EA using a reference frame and its shifted version, which allows us to apply the operation to each token individually. This makes the operation inherently equivariant for any deformation. We note that this mechanism resembles cross-frame attention, CFA, used in video processing, but we emphasize the importance of incorporating EA with an equivariance loss during training to effectively address aliasing effects. In our ablation study, we first train the alias-free VAE, AF-VAE, on a dataset of 256 by 256 images from ImageNet, using weights from the Stable Diffusion VAE. We then train an unconstrained AFLDM in the latent space of AF-VAE on 256 by 256 FFHQ images from scratch. To evaluate the fractional shift equivariance of our models, we compute a metric called shift-PSNR, SPSNR, which correlates positively with shift equivariance. For the VAE, we assess quality using reconstruction PSNR and FID, while shift-equivariance is measured through encoder and decoder SPSNR. The encoder SPSNR checks if the VAE latents are properly band-limited, and the decoder SPSNR evaluates output consistency under input shifts. We compute these metrics on 50,000 validation images. Our results show that ideal sampling and filtered nonlinearity enhance VAE shift equivariance, although both SPSNR values decrease compared to a randomly initialized model, likely due to imperfect anti-aliasing. Adding an equivariance loss helps balance task quality with high shift equivariance, but applying it without anti-aliasing significantly lowers reconstruction quality. For LDM quality evaluation, we use FID on 50,000 samples generated with 50 DDIM steps. We measure LDM shift equivariance through latent and image SPSNR, focusing on the denoising process and the overall output. We find that while LDM with SDVAE has good SPSNR, it suffers from quality degradation in fractional shifts. Using AFVAE improves shifted frame quality, but issues like texture sticking persist. Adding equivariance loss addresses these problems, and by applying CFA in this loss, our final model, AFLDM, achieves the best overall shift equivariance. To further illustrate the advantages of our AFLDM over standard LDM, we evaluate SPSNR at each denoising step. We observe that in standard LDM, shift equivariance degrades due to error accumulation, while our AFLDM maintains higher shift equivariance throughout the process. Lastly, we verify consistent shift equivariance under fractional shifts by horizontally shifting a set of images and computing the average SPSNR for each step. Our alias-free models show higher average SPSNR and lower variance, leading to more stable outputs compared to baseline models. Section Summary. In this section, we introduce equivariant attention, EA, which redefines self-attention to ensure equivariance under any relative shifts by applying a pointwise operation to each token, addressing limitations of traditional self-attention in handling cropped shifts and deformations. We also present an ablation study demonstrating that our alias-free models, trained with equivariance loss, achieve improved shift equivariance and quality in both variational autoencoders, VAE, and latent diffusion models, LDM. Section: Warping equivariant video editing. In this section, we discuss our advancements in video editing through a more stable generation process using our alias-free latent diffusion model, AFLDM, which enhances temporal consistency. To demonstrate this, we created an alias-free stable diffusion, AFSD, by combining AFVAE, modifications to the anti-alias UNet, and retraining the text-conditioned latent diffusion model on the LAION Aesthetic 6.5 Plus dataset. We then introduced a straightforward warping equivariant video editing algorithm. Although AFSD is tailored for pixel shift equivariance, it also performs effectively with irregular pixel shifts, like flow warping, as shown in our experiments. The quantitative results indicate that AFSD outperforms standard stable diffusion, SD, in preserving deformation information, which is particularly beneficial for inversion-based video editing. This means that even if we change the reconstruction process, the diffusion model can still produce consistent results by leveraging deformation information from the latent space. We propose a new warping equivariant video editing method. First, we apply DDIM inversion to the input video, reaching an intermediate denoising time step with an empty prompt. Then, we regenerate a video from the inverted latents using a new prompt, enabling CFA in both steps. This approach allows us to deform noisy latents implicitly without explicit latent warping. Our results show that AFSD's robust inversion and generation lead to more consistent edited videos compared to SD. Next, we explore image-to-image translation, specifically super-resolution using latent I-squared sulfur monoboride. This model directly transforms one image distribution to another without passing through Gaussian noise. We implemented two versions of I2SB for 4 times super-resolution in latent space, one based on LDM and the other on AFLDM. Our findings reveal that the standard latent I² SB suffers from flickering and quality loss with input shifts, while the alias-free variant maintains strong shift equivariance, yielding consistent outputs. We also addressed normal estimation, another image-to-image task requiring consistent outputs across shifts. We implemented a one-step conditional diffusion model called You Only Sample Once, YOSO, which adapts a pre-trained stable diffusion model into a normal map prediction model using ControlNet. We opted for x_0 parameterization instead of x_t, allowing us to avoid a second-stage refinement model. We first trained a baseline YOSO initialized from SD, then enhanced its ControlNet with our anti-alias designs to create an alias-free YOSO, AF-YOSO, based on AFSD. Our comparisons show that while the baseline YOSO produces mostly consistent outputs, some flickering persists, especially around high-frequency textures. In contrast, AF-YOSO achieves fully consistent results across the entire image, effectively reducing flickering.